RMS and effective values. Let's review that carefully. Originally, power systems were DC systems, of course, and the instruments used to measure currents were D'Arsonval instruments, instruments that mechanically determined the average of the currents going through them, and they were perfect to measure DC currents. They were finding the mean or average of currents through them, perfect for DC. When AC systems appeared, engineers of course try to use the same instruments. They try to use them to measure sinusoidal currents. Guess what they got? The average of a sinusoidal current. What is the average of a sinusoidal current? You tell me. Oh, it's zero, of course. They measured zero because the average of a sinusoidal current is zero. One of them said, what if before measuring, that is before finding the average, I square the wave. I square the wave electromagnetically, it's easy to do, and then I pass that through the instrument to find the average of that square. That way I'm not going to get a positive, a zero number, I'm going to get a positive number, right? So the average of a sinusoidal wave is zero. We square that like this, and then we take the average of that, which is the integral over a period t, and we divide by t, the size of the period. A second person looked at him and said, Joe, that seemed like the right thing to do, but now you haven't got amps anymore. Now you're measuring square amps. And Joe said, oh, piece of cake. Let's take the square root of the measure like so, and we have amps all over again. Oh, let's see. What we're doing is we take the root of the mean of the square of the current we want to measure, right? Yeah, right. And that number is non-zero. And that is the number associated to the time varying current. Quite a trick. Does it come with some physical meaning? Well, we'll see. For now, let's call that root mean square, RMS value of the current. Let's recap. To find the RMS value of a current or a voltage or any function of time, f of t for that matter, f of t, this is what we do. We square that function of time like so. And then we find the average or mean of that squared wave like so. We integrate it over a period t, over this period t, and then we divide the whole thing by the size of a period t. And after that, we take the square root of that average like so. That is the RMS value of the function of time, f of t. Any physical meaning? There is something called the effective value that has a physical meaning. The effective value of a current I of t, which is a function of time, we're going to write that as IF like so. IF is the effective value. It's defined as a DC current that transports the same amount of energy in the same period of time as the original current I of t. That is, we find a DC current IFF that carries the same amount of energy in the same amount of period, and as I of t we call that the effective value of the current. Experimentally, we can do that. We come up with a bucket of water, a resistor R, a chronometer and a thermometer, and we measure by how many degrees the temperature goes up in a given amount of time. And then we repeat the experiment with a series of different DC currents, and when we get the same temperature in the same period as in this case, we say this found DC current is the effective value of I of t. Quite convoluted, right? Quite laborious. Our question is, can we determine this IDC, this IFF, mathematically? Oh, you bet we can. Why? Because heating is proportional to the average power dissipated. And for a DC current IDC or IF, the power in the resistor R is R IDC square. And on the other hand, the actual current I of t has an average power that is computed like this: instantaneous power Ri square, average over a period. But for the IDC to be the effective value of I of t, those two powers have to be the same. From there we solve IDC, and we said the effective value IDC of the current I of t is actually the square root of the mean of the square of the current. Wait a minute! The effective value of a current is its RMS value as well, a very important value. Let's find the effective or RMS value of a sinusoidal current written like this. I of t has a peak value, I peak, and is sine omega t plus theta amps. To find that, we use our formula, and using the formula we come up with that the effective value of a sinusoidal current with a peak value I peak is I peak divided by root 2. This is approximately 70% of the peak value of the current. I peak divided root 2. Pretty simple, eh? Pretty simple. Well, from now on, a sinusoidal current used to be written like this. I of t has a peak or amplitude value A. But the effective value of that current is A divided by root 2, right? We call M the effective value of that current. And from now on, in power, we write this sinusoidal current I of t rather like this. I of t is root 2 times M sine, etc., etc., etc. So we explicitly write the RMS value of the sinusoidal current in our expressions most of the time. Root 2 times the RMS value of the current. That's the way we're going to write the amplitude. AC voltmeters and AC ammeters are so that they measure the RMS value of currents and voltages all the time. All the time. So in power systems, every time you hear a voltage or a current number, by default, we are always referring to RMS amps and RMS volts by default. If we want to say something specifically different as peak value or peak to peak, we have to say so. If we don't say so, we're always talking of RMS value. So ignoring this is a serious mistake. Why? Because if we ignore that, we are doubling the power. So it's not a minor error, it's 100% error. That is horrible, all right? If we hear that the voltage is 120 volts, what they mean actually is that the voltage is 120 volts RMS. When we hear that the current is 60 amps, what they mean is 60 amps RMS.